Hello, am I audible?
Yes,
Yes.
yes,
And can you see my screen?
yes.
Okay. So today we will see polynomial regression. So sometimes what happen, we have non-linear relationship in our data, right? So if we want to capture non-linear relationship between input and output, then we cannot use linear regression, right? Because linear regression can only capture linear relationship. So for that we will use non-linear, non-linear model, or we will use polynomial regression, right? So polynomial is a non-linear model, right? Yes. So linear relationship means uh, plane, line, or hyperplane, all are the linear model, right? So if we are learning line, plane, or hyperplane, which means we are learning a linear relationship between input and output, right? So let's say if the relationship between input and output is like quadratic, right? Then we have to learn a quadratic equation, right? So polynomial we will fit there to capture that non-linear relationship. So for example, this is an example of quadratic equation, right? Y is equal to x square minus x minus 2. So if we have such type of relationship between input and output, then we can use quadratic equations. But yes, we cannot fit here a straight line, right? If we fit a straight line, then error will be high, right? RMAC error will be high, or the accuracy will be low here, right? So error will be high if we fit a linear model, uh, but the relationship in data is non-linear, right? Yes. So then how can we fit this kind of non-linear data? So answer is simple. We can use, we can fit a non-linear model, right? Okay. Now, there are two ways to do to fit a nonlinear model. What you can do, you can yes, yes. In first method, what you can do, you can create a nonlinear feature, right? So suppose input features are given to you, right? So suppose x1 is a feature, x2 is a feature, x3 is a feature, right? So what you will do, you will use three feature given feature, right? So originally we are only having three feature in our input, x1, x2, and x3. Now using these three features, we will create a new features, right? So we will create, so depending upon what type of polynomial we want to use. So suppose if we want 2 degree 2 polynomial, then we will create the degree 2 term using given original features, right? If we want 3 degree polynomial, then we will create term 3 degree term, we will create 2 degree term, we will create, and 1 degree term we will create, right? So let's say if yes, so for linear model, what type of model we will learn here? We will learn like theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. So this type of model is linear model, right? So here you can see this is degree 1 term, right? Degree 1 term, degree 1 term, and degree 0 term. But let's say if you want to learn degree 2 polynomial, then in degree 2, we will have degree 2 term plus degree 1 term plus degree 0 term, right? Degree 0 term means bias term, right? So what we can do here, so let's say if you want to learn a uh, degree 2 polynomial, right? And for the sake of simplicity, assume we are only having two features, x1, x2, x1, x2. And if you want to learn degree 2 polynomial, then what will be the equations? So theta 0 plus then theta 0 bias term. So here we are having degree 0 term. Then all degree 1 term we will write here theta 1 x1 plus theta 2 x2. So here degree is 1, right? So degree 0 term, then degree 1 term, then we will write all degree 2 term, right? Theta 3, let's say x1 square plus theta 4 x2 square plus theta 5 x1 x2, right? So if we want to learn degree 2 polynomial, then we will learn this type of equation, right? Okay. Now here there are uh, there are two methods. Either you can directly learn this type of quadratic polynomial, right? So suppose this is your polynomial. Using this polynomial, you will you will calculate the predicted value, and you already have the actual value. So you will use predicted value, actual value. You will create RMSE, right? You will RMSE or MSE. You will calculate for the complete data, and then you will optimize that. Loss, RMSE or MSE loss, right? And after optimizing, you will get the optimal value of these theta values, right? So this is one method. In method one, what you will do? You will use this equation. You will calculate output, predicted output. You already have actual output. You will use predicted and actual. You will calculate RMSE or MSE error. You will optimize. You will use any optimizer, right? So you will minimize that RMSE or MSE, and you will calculate the optimal value of these theta values, right? The other method is, since these two features you already have, so you will add here some more non-linear features, right? So degree 0, right? We already have degree 1, degree 2, sorry, degree 1 we already have from linear model. So what we want? We want degree 2 features, right? Because we want to learn degree 2 polynomial. So these are the degree 2 features. So we will create here three more extra features, right? And we will add these three features, x1 square, x2 square, and x1, x2, and then we will learn a linear model, right? So both approaches are the same. You will get the same answer, right? Because here also you are doing the same thing, right? So you are treating x1 square as a new feature, x2 square as a new feature, x1, x2 as a new feature, and you are thinking like this is some new feature, let's say uh, uh, x3, right? x3, this is square, you can think x4, x1, x2, you can think x5. So it's now theta 0 plus theta 1 x1 plus theta 2 x2, sorry, theta 2 x2 plus theta 3 x3 plus theta 4 x4 plus theta 5 x5, right? So you can think that this is a linear model. If you consider x1 square as a new feature, x2 square as a new feature, x1, x2 as a new feature, right? But these features you are taking degree 2 combinations, right? So like that, if you want to learn a degree 3 polynomial, then you will add degree 2 term, you will add degree 3 term, and then you can apply a linear model, right? Because these features, extra features we are adding, and we are considering these features as a new feature, right? And both are equivalent. Either you can directly learn a nonlinear model, or you can create nonlinear features. You can add nonlinear features, and then you can learn a linear model, right? So here it seems you are learning a linear model, but indirectly you are learning a nonlinear model, right? Because this x3 is not a linear. X3 is in fact x1 square, x4 is x2 square, and x5 is x1 x2, right? Any doubt here? So if you are learning a polynomial, then this type of regression is called polynomial regression, right? Okay. So let's test it. So what we will do, we will first create a nonlinear data, right? So to create a nonlinear data, I'm using this equation. So y is equal to 0.5 x1 square plus 1 x1 plus 2, right? So degree 0 term, degree 1 term, and degree 2 terms, so, right? So and here we are only having one feature x1, right? And y is the output and input is the x1, right? In input we are only having one features, right? So here we are adding Gaussian noise, just we did for the linear case, right? There also we added some noise, right? So we are adding this noise, and we know that this is a quadratic equation, right? So degree 2 polynomial we can fit here, right? Okay. So yes, so the code is same, right? Because same code we have used for the linear case, right? So as you can see here now, this data is having no linear relationship, right? Or in fact, degree 2 polynomial we can fit here, because we cannot fit a straight line here, right? If we fit a straight line, RMSE error will be very large, right? So for that we need to fit a non-linear model, because in input output relationship here is non-linear, right? Okay, so here we are using the second method. What we will do, originally how many features we are having in our data? We are only having one feature x1, right? Now what we want to fit a degree 2 polynomial. So we will add here non-linear features, right? So we will use polynomial feature class to transform the training data, right? Because originally we are only having one feature x1. We will add polynomial features, and now we will learn a linear model considering all new features, right? So new features will include all existing features plus newly created non-linear features, right? Okay. So in this example, let's say if we want to fit a degree 2 polynomial, then here we will write degree is equal to 2. So degree is equal to 2 means it will add here degree 2 features, right? So here in input, we are only having one feature x1, so it will add x1 square, right? Any doubt here? Yes. But let's say if you write here degree 3, then what it will do? It will add degree 3 features, degree 2 features, right? And degree 0, degree 1, degree 0 is a biased term. Degree 1 features are nothing but the original features that we are having, right? Yes. So here we will import polynomial features from scikit-learn pre-processing, and then we will use polynomial features to create non-linear features, right? To create degree 2 features, right? And include bias is equal to false if we don't want to include bias. If we want to add bias, then you can write here include bias is equal to true, right? And then we will fit here we will input data x, and it will give us the polynomial features, right? Yes. So here originally we are only having one feature x1, right? One feature x1. Yes, so here we are printing the first data uh, from our training data set. So originally we are having only one feature, but after adding polynomial features, we are getting one more extra feature, and this feature is nothing but the x1 square, right? Originally we are having x1, and this we are getting x1 square. So now we are having two feature x1 and x1 square, right? Yes. So polynomial feature is degree d. What it will do, it will transfer an array containing originally n features into an array of factorial n plus d divided by factorial d plus factorial n number of features, right? Because it will add no linear features, right? So some new features it will add, right? So for example, here originally we are having x1, but it will also add x1 square because we are using degree 2 polynomial, right? Yes. So this I have already discussed, right? Polynomial regression is capable to find non-linear relationship, right? Where we cannot use linear models. In that case, we can use polynomial relationship, right? Because here we are adding polynomial features, so therefore now we can capture no linear relationship present in the data, right? Yes. So this I have already discussed, right? If we write degree 3, it will add degree 2 term, degree 3 term, right? So if A and B are the original features, A square, B square, A cube, B cube, A square, B, AB square. So these types of degree 2 or degree 3 term it will add, right? So extra features we will create, we will add, and then we will learn a linear model. Yes. So since now we will learn a linear model, so we will use linear regression, and then we will fit the newly created features, right? So here x underscore poly means all features. So x underscore poly will contain old features plus as well as the newly created features, right? Yes. So new features, in new features we will have all existing features plus newly created features, right? So if degree is equal to 2, then x poly will contain both features, right? Original features plus degree 2 term features, right? Okay. Then if you fit a linear model using by putting any doubt?
Yeah, sir. Where we create this xpoly object? Hello.
No. X poly here we are getting, right?
Okay. Okay.
Hmm. Because originally we are only having one features, right? We are only having x1 features, and we
Hmm.
want to fit a polynomial of degree 2. So we have to add degree 2 term in input, right? So x1 square we have to add. So for
By
that,
the
yes, we
okay,
will
by
use
the
polynomial.
polynomial we create xpoly, then put to the linear function.
Yes, because x poly will contain degree 1 features, degree 2 features,
Okay. Okay.
right? So
Right.
yes, so here this is the original feature, right? X1, and this is the newly created feature x1 square, right? Now using these features, now we have two features, right? X1 and x1 square. Now we will train here the linear model, right? So it seems like we are training a linear model, but indirectly we are training a non-linear model, right? Because in input we are having x1 term, x1 square term, right? So it's a non-linear model. Yes. So because we are not learning a linear model on original input, right? Originally what input we are having x, right? X is the original feature, right? Using this original feature x, we are created new features, right? And new features we are already having existing features plus newly created features, right? So x1 is already there plus x1 square newly created features, no linear feature, right?
If my equation is the x3, then convert, I change the degree, then return back the 3 coordinate, right?
Yes. In that case, it will return x1 square, x1 cube. If we have
3D.
only one, originally we are only having one features, right? But let's say if we have two features, let's say a and b, then it will add a, it will add b, it will add a square, b square, ab term will be there. Then a square b, then ab square, then a cube, b cube. So it will add all such terms there, right? Degree 3 term, degree 2 terms in all combination, degree 1, right?
Okay.
So now, as you can see here, we are learning a linear model on newly created features, right? So if you write here x original features x, then you are learning a linear model. But since here we are using x underscore poly contain all terms up to the degree that we have already defined. So if degree 3, then degree 3 term, degree 2 term, degree 1 term, and degree 0 term, right? So indirectly we are learning a non-linear model here, right? Okay. So originally we are having x1, but we are learning a linear model using this type of data where we are having x1 square. So this type of model we are learning, right? Where we are having degree 2 term, degree 1 term, and degree 0 term biased term, right?
Sir, I have a question.
Yes, yes.
How we will determine, like, because if we have only one feature, then we are saying x square plus and
Mhm.
x1. But if we, is it possible to have it x cube? How will decide? Like, we'll have only the x square plus x1 and
Mhm.
the constant.
Yes, yes.
What's mm-hmm.
So, in fact, if you can visualize the data, then we can decide, right? Because here this polynomial has very simple property. So, for example, degree one polynomial. Degree one polynomial means straight line, right? So, degree one polynomial or straight line is something like this, right? So straight line, how many times this straight line will bend? 0 time, right? So if we have the linear data, then we can use a straight line. This is a degree 2 polynomial. Degree 2 polynomial can bend 1 time, right? Can change its direction 1 time. So as you can see here, now from this point, it is changing its direction, right? If you take degree 3 polynomial, it will change its direction 2 times. So here we are changing direction 1 time, here we are changing. So it's a degree 3. Similarly, degree n degree polynomial will change. If you take degree is equal to n, it will change its direction n minus 1 time, right? So you can use this fact to know a priori what type of what degree of polynomial we can fit, or if we don't know anything about the data, if we don't know, if we are unable to visualize data, then what we can do, we can generally fit a very high degree term. So let's say we can use degree 5 term, degree 5 polynomial, or let's say degree 7 polynomial, and then we can use regularization to prevent overfitting, right? So for example, what you can do here, you can fit here even degree 5 polynomial, right? So if you fit a degree 5 polynomial will bend here 4 times, right? So it will overfit, the model will be overfitted to your data, right? So then what you can do, you can use regularization technique, you can use overfitting preventing technique to avoid overfitting, right? So let's say if you are using regularization, what regularization will do? Regularization will penalize coefficient of polynomial term in such a way the model now will become smooth, right? So regularization I will discuss later, but yes, what we can do in that case, we can always have a higher degree term, because we cannot, if we are taking a lower degree term, then we may not be able to capture the relationship between input and output, and then what will then happen that we will get a very poor error, very poor accuracy, right? So error will be very high if we are not fitting a correct model. So we will start with the high degree polynomial, and then we will use regularization. And regularization will penalize our model in such a way, some coefficient it will make, become to 0, so that ki model will become smooth, right?
And what are the, like, what are the use case of this in
Yes,
practical
so
knowledge?
yeah, so practical use cases, sometimes, so let's say whenever we are having a non-linear relationship between input and output, then we can use a non-linear regression model, right? Because linear will not work here.
Sir, here one my question here is how to identify that the input or output is the linear or non-linear.
No. We will, in fact, we don't care. We will learn a degree D polynomial, and we will use regularization.
So that means we can predict in the first time कि this model is work or not.
Okay. So let's say you are fitting here. You are fitting here a non-linear. You are fitting here a polynomial, right? Now this 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 polynomial is a 300 degree polynomial, right? So 300 degree polynomial will bend 299 time, can bend 299 time, right? So as you can see here, if you fit 300 degree polynomial, it will overfit, right? It will try to fit each and every data. So let's say if you are having some data here, it will also fit the data also, right? So it will fit all outlier, all noise present in data, it will fit, right? If you fit a linear model will not work here, right? Because data is, so ideal model here is the degree 2 polynomial, right? Okay. So what you can, but a priori we don't know, right? We don't know what type of model we should use here. So what we will start with, let's say you are starting with the degree or let's say, let's take a very simple example. Suppose the input output relationship is linear, right? Even if the input output relationship is linear, it will penalize. Okay, so let me take a linear example, because here if we are fitting degree 5 polynomial, then in degree 5 there will be lots of term, right? So it may confuse you. So let me take a linear example here. Yes. Yes. So suppose this type of data we are having, and here you are fitting a polynomial of degree 2, right? Now, what relationship we are trying to fit here? Y is equal to theta 0 plus theta 1 x1, because we are only having one feature x1, right? Plus theta 2 x2 square, right? So here what we will do, we will put a so originally we are having one loss function, right? RMAC we are having, plus we will add some regularization term here. And that regulation term, what it will do, it will penalize these values. It will penalize theta 1, theta 2, and so it will penalize solution. It will penalize unknowns in such a way that these has to be as small as possible, theta 1, theta 2, right? So even if you are having, let's say, y is equal to theta 0, theta 1 times x1, and let's say this the regularization is penalizing theta 2 in such a way that value of theta 2 is, let's say, 10 raised to power minus 7. So 10 raised to power minus 7 times x1 square, right? So since this coefficient is very small, so this term you can neglect, right? This term is, so indirectly you are learning a linear model, right? So it's not a non-linear model, because this higher order coefficient is very small. It tends to 0, right? And why it is tends to 0? Because optimizer will penalize this coefficient theta 2, right? Because this theta 2 is not required for this data, right? So it will penalize theta 1, theta 2, but yes, it cannot penalize theta 1. If it penalize theta 1, the error will be increased. The error will get increased, right? So to prevent this case, it will only penalize theta 2, right? So using regularization, we can fix this problem, right? Because here a priori we don't know. So if you visualize this data, then because since it's a toy example, you can easily identify that a linear model will fit. But in general, let's say you don't know anything, then you can start with the higher order polynomial, and you can use regularization. Regulation will penalize higher degree coefficient in such a way that these higher degree coefficient will become very small, right? If they are not needed, right? So for example, in this case, theta 2 is not needed, so theta 2 will become small. So it's a job of regularization to make theta 2 very small, right? Any other doubt?
If let's say we have a degree 2 polynomial, so there is one option that we start with linear and then go to degree 2.
No. Then you have to search several models, right? You will train multiple. So that option you can also try. You can start with degree 0, degree 1, degree 2, degree 3, and whatever model is giving the best performance, you will choose that model.
Yeah, so my question was exactly that if let's say we train a higher degree model, let's say degree 5, we start with degree 5, then the cost of training such a model will be higher because the calculation will be more complex.
Yes. So then you can use the second approach, right? You can directly train higher order degree term, but just use the regularization term. Regularization will automatically penalize higher degree coefficient.
So is it better to start with higher degree and then come down, or start with lower and then?
No. We don't care. Higher degree coefficient will become automatically 0 if higher degree terms are not required.
So in terms of training cost, which approach works better?
No, if we are considering only one model, then definitely the model that is having less feature will train faster, right? Because then we don't have to do extra calculations, right? If you only have x1 term, then calculation will be easy. If you are having some more extra term, x1 square, x1 cube, then that will increase our computations, right? So that will slow down our model, right? But if you are searching 100 model, then selecting one model, and other case you are adding some extra features and using regularization, then definitely the training time will be less as compared to training 100 model, right?
Okay, so how do you decide what degree to start?
Generally, people start 5-7 degree term because rarely we will use 100-degree, 200-degree polynomial, right?
Okay, so you can start with around 5 and then use regularization.
Yes, but actually we don't know anything about data if we are dealing with the high dimensional degree data. So then we will use cross validation, right? So again, we will try some random degree polynomial. So for example, 10-degree you can start. So let's say if using 5-degree or 3-degree you are getting best performance, you can stop there, right? Because uh, it depends on how much error you can tolerate, right? If using, let's say, you have tried degree 5 polynomial and error is below the that what you can tolerate. So let's say if epsilon is the your criteria, that error has to be less than epsilon, and if you are getting less than epsilon, you can stop there, right? But if you are not getting, then we have to try other options also, right? Because if you are using degree 5 polynomial, but let's say you really want degree 100 polynomial, then regularization will also not work there, right? Because regularization can only come down degree 5 to lower degree polynomial. It cannot increase the degree, right? So then we don't have any options, and we have to try several other possible options also, right? So you will try degree 5, you will try degree 10, you can try degree 20, right?
Practically, most of them will fit around degree 5 to 7. That's what you're saying with regularization.
Yes, yes. No. So regularization will automatically reduce the degree of the polynomial that we are starting, right? But why are not we starting with the degree 100 polynomial or degree 200 polynomial? Because if you are taking degree 100 polynomial, then it will create so many features. It will add so many features to the original number. So originally, let's say we are having 5 features, it will add so many terms in our data, right? So then the training or testing will become very slow, right? Okay, so here let's say if you add degree 2 polynomial term, then you end up learning this type of model, right? Now this 0.56, 0.93, and 1.78, these optimal weights we will get using optimizations, right? So either directly you can so you will use some optimizer, you will minimize MAC, or so let's say if you are taking MAC loss, so MAC loss will be minimum if you use these values 0.56, 0.93, 1.78, and it is same just we did for the linear case, right? Okay, so finally you end up learning this type of model, right? So it's a degree 2 polynomial, and as you can see here, if you fit degree 2 polynomial, then error will be lowest, right? Okay, so any doubt here? So even if you fit here degree 3 degree 3 polynomial, directly you cannot use degree 3, you have to add regularization term also, right? Because if you fit degree 3, degree 3 will bend. So what happens, let's say even if you are using x1 cube, the coefficient has to be very small, right? So then what happen that the model will become smooth, right? So in regularization we will do exactly, right? So regularization I will cover. So there we will see higher order term, it will penalize, right? Regulation will penalize to prevent overfitting. Okay, so let's now discuss learning curves. So in learning curves, what we do, so higher degree polynomial fit the training data, much better than the plain linear regression if we are having no linear relationship, right? Because we cannot capture no linear relationship using linear models, right? So we can fit a so let's say this example. In this example, we are fitting a degree 1 polynomial. Degree 1 means line, straight line. Degree 2 polynomial, right, parabola, and degree 300 polynomial. So as you can see here, this 300 degree polynomial clearly is overfitting, right? Because here this 300 degree polynomial is trying to fit every point, every data points, right? Okay, so here the correct option is to use the degree 2 polynomial, right? Okay. So plain model, degree 2 polynomial and degree 300 polynomial, right? Okay. So as we can see in previous diagram that um, uh, that the 300 degree polynomial trying to fit each and every data points and will also fit model noise present in the data. So it will create a overfitting problem, right? So high degree polynomial model is severely overfitted to the training data, and the linear model is underfitting, right? Because this model is too simple, right? So here, so underfitting, overfitting, I've already discussed, right? So if you use linear model here, underfitting will happen. If you use the 300 degree polynomial, overfitting will happen, right? Right? So underfitting means when the training error is also high and the test error is also test or validation error is also very high, right? So both training and testing error are high in case of underfitting. In case of overfitting, training error is low, but the test or validation error is high, right? So since this 300 degree polynomial is fitting each and every point perfectly, so therefore training error will be less, but this model is clearly is not generalizable, so test error will be high, right? So here, if you use 300, it will create overfitting problem, right? And this for this linear model, even this model cannot fit the training data very well, right? So if you use this linear model, training error will be high, test error will be high, right? Okay. So now the question is, how do we find model is overfitting or underfitting underfitting the training data? So you can simply calculate the training error or the testing error, and you can use the cross validation to calculate to decide whether whether underfitting or overfitting is there or not, right? Okay. So what we will do, we will yes, and conditions I have already discussed, right? So if model performs well on the training data, which means the training error is very less, training error is very less, or the training accuracy is very high, training performance is very high, but the test error or the test performance or validation performance is poor, then the model is overfitting. Overfitting means we are using too complex model. Data is not that much complex, and we are using too complex model. So, for example, here, right? So, data is not so complex, and we are fitting here 300 degree polynomial, right? Underfitting means model is too simple. So, let's say this quadratic relationship we are having originally, but we are fitting a very simple model. We are fitting a very basic model, right? So, so that will result in underfitting problem, right? So underfitting means model is too simple. If you use too simple model, then underfitting will be there. If you use too complex model, then overfitting will be there, right? And we will use training accuracy. We will use validation or test accuracy, or you can use error also, right? Training error or test or validation error to check whether overfitting is there or underfitting is there, right? Yes. So another approach is to use the learning curve, right? So first approach is we can use cross validation. So cross validation we have already discussed, right? So you can use cross validation to know to calculate to know whether underfitting is there or overfitting is there. The other option is we can use learning curve. So learning curve means we will plot model performance uh, on training set and validation set, right? As a function of training set size. So what we will do here, x-axis we will take variable training set size, right? So for example, let's say originally we are having 100 training points. We are having 100 training points in our data set. What we will do, we will only pick 10 points and train model. We will pick 20 points and train our model. We will pick 30 points out of 100 points and we will train our model. So likewise here we will create we will choose variable number of training points and we will train our model, and then we will create training performance and the validation performance. So we will draw this curve, and this curve is called the learning curve, right? So learning curve are nothing but the plot of model performance, right, on the training set and validation set as a function of training set size, right? So here we are plotting as a function of training set size, right? So originally, let's say assume we are having 100 training data and we are randomly selecting some data points, and we are calculating validation accuracy or training performance or validation performance. So this type of plot is called the learning curve, right? Okay. So to generate a learning curve, we will simply train the model on different sized subset of training set, right? So we will plot learning curve. So here, let's say if the problem is we are solving a linear regression model. So for linear regression model, if let's say we are having originally having 100 training points, and if you pick randomly, and if you calculate training and validation performance here, so you will get this type of curve, right? So this curve is a learning curve. Now, using this curve very easily, you can calculate overfitting or underfitting, right? So how now how can you calculate underfitting or overfitting if you are given this type of learning curve? Can you answer? So RMAC is a error. RMAC is a error, right? So if overfitting is there, then what will happen? So this red means the training error, right? If overfitting is there, then training error will be small, right? Training error will be small and validation error will be high. And if underfitting is there, then training error will be high. At the same time, test error will be high, right? Okay, right? So for let's say if we are having underfitting, then training as well as the validation, both error will be high, right? If we are having overfitting issue, then training error will be low and validation error will be high, right? Okay. So let's say if you are doing linear regression, if you are training linear regression model on different training set size, and if you plot curve, right? So so now let's visualize this learning curve. So here when we are only having very few instances, for example, only one or two instances in the training set, then model can perfectly fit them, right? Model can perfectly fit them if we are having only very few instances are there, one or two, right? Okay. Yes. So first of all, here we are learning a linear regression model, which means we are learning a linear model, right? Okay. Now assume you are only having one data point. Now this one data point you can fit any line, right? So this line also fit this data point. This line also fit. So in fact, there can be infinite many line using which you can fit this one data point, right? So that's why the training error, right? So training error is zero, right? Because perfectly you can fit one data point using any straight line, right? That passes through that point, right? So this line also pass through this training data point. So training error will be zero. You can also use this line, right? But the validation error will become very high because here using one data points we cannot predict a line, right? Okay. So when there are just one or two instances in the training set, the model can fit them perfectly, which means the training error here is very less, right? But at the same time, we will have a high validation error, right? Okay. Yes. But as you add more and more data point to the training set, it become impossible for model to fit the training data perfectly, right? So if you are adding more and more data points, let's say you are adding more points, right? So now a linear model cannot perfectly fit all these data points, right? Even let's say we are using this linear model, so there will be some error, right? So now it cannot fit uh, training data perfectly. So as you can see here, if we are increasing number of data points, if we are increasing number of data points, the training error is increasing, right? But at the same time, this validation error is decreasing, right? Because now we are sure that this can be the line, right? Because if we are having so many points, then definitely we can say that the model has to be in this direction, right? If we are only having one single point, so let's say we are only having this point, right? Now for by just using single point, uh, infinite many line can fit here, right? So this line will also fit, this line will also fit, this line can also fit, right? This line can also fit. So that's why we will have a very high validation error when we are having only few data points. But as you add more and more data point, the validation the validation error will decrease, right? Because now we know that this can be the optimal model, right? Yes. So yes. And the error on the training data goes up until it reaches a plateau, right? So as you can see here, the training error now has stabilized, right? The validation error is also stabilized, right? So uh, now after this point, if you even if you add some more data points, um, uh, it will not change, right? So at that point, adding new instances to the training set, if doesn't make error much better or much worse, then we can stop at that point, right? So for example, here you can see even after after adding 70 data points, even if you add some more data points, you will get similar kind of trend, right?